the celestial theodolite. I don't know if you know that, but he's also anti.
If you prove flat Earth wrong, you'll get banned from QOps. That's what he did to me.
So, Jesse, are we? I guess you're still setting up, maybe. Sounds like you're still formatting. Let's see.
I mean, I guess it would be difficult to recant, to recite something that you maybe don't know. I don't know, because if you've been around the debate long enough, I'm pretty sure if you're listening, there's one good answer. I mean, I guess it would be difficult.
Yeah, looks good, Jesse.
Recant, to recite something that you maybe don't know. I don't know, because if you've been around the debate long enough.
Oh, I see. I've got
if you're listening,
I've got a little problem with my answer. Hold on, let me get rid of I've had the YouTube echoing in my ears, so I had to get rid of that. Okay, now I think I'm set. Okay, so if everybody's hearing me okay, am I too loud? I think I might be a little driven. There. Okay. You sound a little low to me, Jesse. I don't know if due to others, but I think I should be at a pretty good volume. All right. So this is a presentation that I've given a couple of times. I did some pretty significant modifications this time in the light of things that have happened since. I first did this presentation, I think, last March on my I have a club. I'm a Clubhouse guy, and I do a series called The Bite of Physics there. So this was episode 78 of Bite of Physics, and then I revisited it as episode 90 3 months later. So what I've been doing, so I've given it a presentation a couple of times beyond that, and hopefully we'll give it a couple times more in the next week or two. But so this is kind of a practice run on this new version of it. We'll see how it goes. I'm happy to have people ask questions along the way, but I don't want to needlessly extend things. So anyway, getting right into it, going on to the introduction here. Much of this won't be necessary, I think, for people in this room. But at any rate, as you all know, the flat Earth community has generally pushed back against this idea that the sky can tell us anything about the shape of the Earth, which isn't surprising because really virtually every observation of the sky not only argues against, but strictly rules out every conceivable flat Earth model that's not based on magic. And we can go through several of those, but I don't want to spend the time right now. We can do that afterwards if you like. And I give one example there, the 69 miles per degree thing. Anywhere on Earth, you see an object in the sky, if you move 69 miles toward it, 60 nautical miles or 111 kilometers toward it, it will rise by 1 degree in the sky, with a slight exception of if the object is very close to the horizon, where atmospheric refraction starts becoming a bit of a factor. But otherwise, it's true for every celestial object. And it's true at all times. It's true for all starting places. You can start anywhere on the planet, see any celestial object, move 69 miles toward it, and it will rise 1 degree in the sky. And it's pretty trivial, frankly, to show that observation is only possible on a spherical Earth with a radius of about 4,000 miles. So it is noteworthy and a good sign that the flat Earth community, at least a portion of them, have embraced this method for using the sky to address the question of the shape of the Earth, dubbed the celestial theodolite, a reference to the instrument used by surveyors like Jesse I guess Jesse's not technically a surveyor, but he knows his business. And Shoebill, in geodetic surveying, it's an instrument that determines precise azimuth and elevation angles. And I have, from the very start, thought this is, not only is it great that it uses the sky to determine the shape of the Earth, but because it comes from the flat Earth community itself, it's easily executed, requires no expensive equipment, and it does very much indeed tell us about the shape of the Earth if it's executed correctly. I'll talk a little bit more later about the difference between kind of the approach. Jesse, I think most of you know, has done an awesome job of taking the copious data that's been produced and analyzing that. But I'm going to take a different approach and just talk about the fundamentals of the idea, and how it works and how simple it is to use it to come to very clear conclusions without really even looking at anything beyond the first data point that that Mike Heffron took back in the last day of January of last year. So what is a celestial theodolite? Simply put, it uses stars to determine the visual elevation angle of distant mountain peaks. And it requires the observer to determine only the time at which a star sets or emerges from behind the peak. That's it. And then a way to find out what the elevation of that star was at that time. That's really, really it. The first part's pretty easy. It's not that easy. It's not as easy as one might hope. But with a good telescope or patience or something, you can watch a star descend toward a peak on the western horizon, and within a second or two determine the time at which it blinks out behind that peak, which gives you the time at which it's visually at that same place. And then the only question is, how are you going to find out what the elevation of that star was? And that's actually pretty easy, because there's lots of astronomy software that will tell you the elevation angle of a star if you give it your position and you tell it what time it is. And so the CT originators have embraced using the Stellarium software, which is free online software. And why shouldn't they, right? It's not the only thing you could use, but Stellarium's fine. It works. If it didn't work, people wouldn't use it. People use it to find out where they should point their telescope to see something, and it tells them accurately. Okay, so what is a recap of the idea? I think it's nice to see this picture here to really appreciate that what you're doing is you're looking at it for a time when a star appears at exactly the same place as a peak, and you simply jot down that time. You do have to know what the star is. That sometimes is not completely trivial, as Jesse probably can tell you, but it's not too hard. Especially if you have a video and you see some neighboring stars, you can find a star chart and figure out what the star is. And then use Stellarium to find the visual elevation angle of the star at that time. That's it. Easy peasy. Let me stop just for a second. Any comments or questions yet? Okay. So what does that have to do with the shape of the Earth? And the answer is that fundamentally, the question any theodolite settles in this regard is whether or not there's a thing called globe drop. Real theodolites are expensive, so not many people have them. Few people are willing to go out and buy one to do this. But the answer is the question that you're answering is there globe drop? On a flat Earth, the elevation angle of a distant peak is simply determined by how much higher it is than the observer and how far away it is. And so you can see down there at the bottom left, distance to the peak, the height of the peak relative to the observer, so the difference in the elevations. And that geometric angle is just given by the arctangent, the angle whose tangent is the height divided by the distance. It's that simple. But on a globe Earth, it's made a little more complicated because the elevation angle is slightly smaller due to globe drop. And you can see over there at the bottom right how the curvature of the Earth means that the base of the mountain is a little lower by a distance called the globe drop. And that globe drop is given by the distance to the mountain squared divided by twice the Earth's radius. That's pretty simple geometry, Pythagorean theorem type stuff. And then the geometric elevation is just the arctangent. This time, rather than the height divided by the distance, the height minus the globe drop, because that now becomes the opposite side of that right triangle that you see with the dashed line on the lower right. So you have to subtract the globe drop from the height. That gives you a smaller angle. And so the only question is, which one is right? Assuming you can answer that. Sometimes you can't answer that with perfect clarity, just because there's always uncertainties involved. So we'll have to take into account uncertainties when we evaluate things. But it turns out that in this case, the uncertainties are small enough that the answer is pretty clear, as we'll see. So I want to talk right away about the original observation that led to this whole celestial theodolite, which is an observation that Mike Heffron made of an occlusion of the star 39 Aquarii from his house, 50.6 kilometers away from Pikes Peak, on January 31st at 6:27:25, 25 seconds past 27 minutes past 6 p.m. local time. So he observed that the star 39 Aquarii disappeared behind Pikes Peak at that instant. And there's a picture from a video that he has that he used to determine this. You can kind of see what it looks like there. You can tell it's Pikes Peak because you can actually see the lights of the visitor center, and you can see the star basically at the same height as the visitor center. The top of Pikes Peak is relatively flat over that range. 39 Aquarii is just over a little bit north of the visitor center, a little bit to the right in this picture setting. It's come down at an angle, stars set coming down, slanting down toward the north. So it has come down from above the visitor center down to that point. And everybody agrees that the distance to Pikes Peak from Mike Heffron's house is 50,646, give or take a few meters, give or take maybe 10 or 20 or maybe 100, I don't know. And that the elevation of Mike Heffron's house is 2,070 meters, and the elevation of the peak of Pikes Peak is 4,300 meters. Once again, give or take a few meters. And if you work out what those give or takes give you, they're going to give you a little bit of uncertainty in the angles, an uncertainty that's significantly less than 1 minute of arc. So on a flat Earth, you find that the angle, the geometric angle from Mike Heffron's house to the top of Pikes Peak is 2 degrees, 31.3 arc minutes. Now, I wouldn't put too much faith on that 0.3. It might be 0.1, 0.2. There's some uncertainty at the level of tenths of a minute, but not much. It's clearly closer to 231 than it is to 232 or 230. And similarly, on the globe Earth, because of the globe drop, the drop turns out to be 201 meters. Once again, give or take a meter or two. And if you subtract that from the elevation difference, you now take the arctangent of 2029 rather than 2230 divided by 5646. And you get an angle, a geometric angle, elevation angle of 2 degrees, 17.7 arc minutes, with the same kind of uncertainty, an uncertainty at the tenths of a minute level, some fraction of 1 minute. And he saw that happen at 25 seconds past 27 minutes past 6 p.m. on 31 January 2025. And if you simply plug the location of his house into Stellarium, and you ask Stellarium what was the elevation of 39 Aquarii at that time, it tells you 2 degrees, 18.8 arc minutes. So I would point out that obviously already we see that the number from Stellarium is much, much closer to the globe value than the flat Earth value, but there is some uncertainty at the level of tenths, some number of tenths of a minute there. So is that enough? Is that uncertainty enough to cover it? I don't know. It's more than a minute off. But on the other hand, so far we haven't taken into account any refraction effects. Well, actually, we have in a disguised way that I'll get back to in a minute when we talk about this angle, the Aquarii angle. But we certainly haven't talked about what refraction may or may not do to the mountain peaks. So I do want to talk about that a little bit. Let me stop because this is an important slide. This is data that I dare say nobody disagrees with. Okay, so what effect does atmospheric refraction have? Okay, so what effect does atmospheric refraction have? And the answer is that atmospheric refraction for any light that's horizontally directed at altitudes well above the ground, I think it's fair to say, always bends downward. There are weird refractive effects that happen near the surface of the ground due to temperature inversions and all sorts of things that can happen because of the temperature of the surface itself. And this is responsible for mirages and fata morgana and a lot of observations of things where it looks like you're seeing things much further away than you should see them. These are always over relatively short distances, and they're also usually over relatively cold water or ice or over hot surfaces like pavement. Lots of things can happen when you're very close to such things. But horizontally directed light is bent downward by refraction toward the higher density air, which is always at lower altitudes in the atmosphere in general. And as a result, the visual elevation of distant objects is lifted by a little bit. I'm showing in the diagram down there that if you imagine a ray of light leaving the peak and ending up in your eye down there at the right at the observation point, that light, because it's curving downward, looks at the very end as if it was coming from a higher angle than it actually came from. The dashed line represents the geometric angles we were talking about before. But that angle is really small. There's very little effect of terrestrial refraction. You really can almost completely ignore it. You certainly can, in this case, ignore it if you're just trying to ask which is closer, globe or flat Earth. But it must be included if you're doing accurate surveying kinds of things. And it's best to include it because it's pretty easy to do. You do it by knowing, because we know how refraction works. It depends on the gradient of the index of refraction. We do this in the lab. So we know how much light curves, horizontal light curves at different altitudes. And at altitudes around Heffron's house, it curves by about 4.5 arc seconds per kilometer, give or take. Once again, something like that. And to determine the lift angle, you end up, if you can understand, I could take you through it if you want, but I'll skip over it pretty quickly. You simply take the total curvature and divide it by 2, because the total lift angle is a result of how much the direction changes from the midpoint of that ray, which is parallel to the direction from the observer to the peak, to the end ray there. So the apparent direction at the midpoint to the apparent direction at the observation point, the lift angle is half of the total curvature of that light ray. So I take the 4.5 arc seconds per kilometer, multiply by 50 kilometers, I get a, and then divide by 2, and I get the amount of terrestrial refraction. It's very small, as we'll see here. So what happens if I include that terrestrial refraction in the previous data? Well, here I've done that. The flat Earth version, both versions, both flat Earth and globe Earth, will have the apparent direction lifted by, I get about 1.7 arc minutes, and say more than 1 and less than 2 arc minutes, probably closer to 2 arc minutes. Yes, I want to chime in here, but I'm trying to be very generous with my uncertainties. I think you would agree that it's something like 1 to 2 arc minutes of terrestrial refraction lift from the peak to the observation point. And it doesn't make much difference. You see, it makes the visual angle to the peak a little higher in both cases. And the result of that is that the agreement between the globe and and what Stellarium says is now closer than it was before. It's now about a half of 1 minute, which is, I would estimate, within the kinds of uncertainties that we're talking about here. So, comments, questions on any of that? Maybe just a shout out to make sure you're hearing me. Somebody assure me that you're actually there.
I am.
Okay, very good. I didn't hear that very well, though. Is that just me? Is that me not having things up? Not sure.
I don't know, because you roboted for just a tiny bit when you were talking. I could hear everything, but I don't know. Maybe Discord is struggling today.
Okay. Do I sound? You're saying I sound too low?
No, just you crackled out a little bit.
Oh,
Just
I see. I see.
for like a minute.
I think I've. Oh, I see. I crapped out. Yeah. Sorry about that.
No, you sound fine.
Okay. Very good. Thank you
Okay,
very much.
so it might be me.
Well, I think it was me a little bit. I was looking at the wrong thing on my mixer for a moment, so it was partially me. All right. So let's move on. So as I say, this is really the final result for Pikes Peak, for that initial observation, and I claim at some level I shouldn't have to say anything more. The visual angle to 39 Aquarii, when it was observed at the same place as Pikes Peak, agrees with the calculated visual angle to Pikes Peak from Mike Heffron's place, and doesn't come anywhere near agreeing with the visual angle, doesn't even come near agreeing with the geometric angle, let alone the visual angle, which is higher yet. So there's an enormous discrepancy between the flat Earth version and what Stellarium says, and basic agreement with the globe. And so at some level it should be done, but you might still ask, well, wait a minute, you refracted the peak. Didn't the star refract too? And in fact, wouldn't you expect the star to refract even more, because you're looking at it through a lot more atmosphere? And the answer is yes, that's exactly right. Stars get lifted much more. Stars near the horizon get lifted much more than a peak will, because the light from it is traveling through much more atmosphere. Starlight from a star near the horizon may enter the atmosphere at a distance of 400, 500 kilometers. And so it travels through much more distance than the light from a peak, has much more distance over which to refract downward. And therefore, by the time you see it, it's going to look significantly higher in the sky. And this diagram from Bennett, this is kind of the classic refraction versus altitude thing. This says that a star, for instance, a star at an apparent altitude of 5 degrees will be refracted upward by about 10 arc minutes at sea level. This is a diagram for the amount of atmospheric astronomical refraction, the amount of refraction the atmosphere creates for astronomical objects at sea level. So if you're at sea level, you see an object at 5 degrees, it'll be refracted upward by about 10 arc minutes, and so on. Now, if you are at a higher altitude, this whole curve lowers a bit, because even at Denver, by the time you're at Denver, there's still nearly half of the atmosphere to have to go through. Well, not half, but 20-30% of the atmosphere is below you, so you haven't gone through as much as you do at sea level. But I want you to notice in particular on this diagram that if you kind of look at the 4 degree, if you say, what would an object at 4 degrees And I'll tell you why I'm interested in that in a moment. An object appearing at 4 degrees will be lifted by something like 12, maybe something like 12 arc minutes. Oops, sorry. At sea level. And so keep that in mind as we do the next thing here in a moment. So did we include this astronomical refraction? And if so, how did we do that? I didn't see us do that. And the answer is that stellarium does that. Stellarium automatically adds astronomical refraction, as it really has to, because stellarium, when you ask stellarium where to point your telescope to see something, it has to get that right. And to get that right for objects near the horizon, it has to apply the astronomical refraction, which is some, significant fraction of a full degree. That's getting to be, similar to the size of the moon, something like that. And it does do that. Stellarium needs you to tell it where you are, where the barometric pressure, what the barometric pressure is. That's tells it how much of that refraction curve it should be using, basically. And the object being observed and what time, because from all of that, it can determine what its geometric angle above the sky is, and then it can determine where it's going to visually appear due to the refraction. So on the next 2 pages, I show a couple of screenshots using stellarium the way the CT guys, the way the flat Earth guys do, that tell us where Arcturus was on 14th of March 2025, observed from Denver, Colorado at 10:30 a.m. local time. Now, it shows all of that because the first time I gave this presentation was on 14th of March at 10:30 a.m. and I had some listeners in Denver, so I wanted to kind of personalize it. The first page is going to show the elevation that the star would be seen at if there were no atmosphere. And the second one will show the elevation that the star is seen at because there is an atmosphere. And this is the kind of thing that the flat Earth guys do, is to turn on and off the atmosphere. So here's the first shot. This is showing what Denver, Colorado looks like at 10:30 in the morning on that date. And you may notice, wait a minute, how is it night? And the answer is, well, it's night because there's no atmosphere. When you turn the atmosphere off, you don't have a blue sky, and you get to see stars everywhere except close to the sun. And so this is kind of a picture of what it would look like. And buried over here in all of this data on the left, you'll find one thing which gives us the piece of information we're interested in. The elevation angle of Arcturus at that time was 4 degrees, almost 7 arc minutes, 4 degrees, 6 minutes, 59.7 arc seconds. But if I turn the atmosphere on, remember that 4 degrees, 7 minutes, basically. If I turn the atmosphere on, all of a sudden the sky is blue, as it would be at 10:30 in the morning. And the altitude angle of Arcturus rises by about a little more than 9 arc minutes. So it goes from 4.7 to 4.16.5 or 4.16.22 arc seconds. So it rises significantly. That's a very noticeable amount of angular difference. And I'll ask you to remember that I just told you that atmospheric refraction was about 12 arc minutes for some object at 4 degrees elevation at sea level. And that's true. At sea level, Arcturus, if Denver were at sea level, the difference between these two numbers would be about 12 arc minutes. But at Denver, because there's not as much atmosphere, stellarium correctly tells you that there's less lift. It only gets lifted by a little more than 9 arc minutes rather than the 12 arc minutes. Anyway, this is probably way more information than you need to know on this. The important point is that stellarium knows how to deal with the atmosphere, and it applies astronomical refraction in order to just simply tell you where you're going to see the star, what angle you have to point your telescope at to see the star. Okay, so having gone through all of that, I'll just return to the fact that it's not clear why there's any continuing fuss. Well, why is there any continuing fuss after this slide? The slide that I showed you before, that the flat Earth predicted visual angle to Pikes Peak is about 233. The globe is about 219. And the visual angle from Stellarium is also about 219. So it seems like the question has been settled pretty clearly and emphatically by this single observation. And of course, you'd want to do more, but this one would have to be very far off for that not to be the case. And so why is there all this continuing fuss? Why aren't the results perfectly clear? And you would think so, but the thing you don't yet know, many of you do, is that proponents of the celestial theodolite, the flat Earth celestial theodolite, do not agree that the time at which the star becomes visually occluded is the time at which its visual elevation is the same as that of the peak. I want to really emphasize that. They do not agree that the visual elevation of the star, the place that we see it, is the same as the visual elevation of the peak, the place that we see it at the moment that they coincide, producing the visual occlusion. So I just want to give you a moment to appreciate the audacity of that claim. They say that it happens at a different time than the time at which the two appear at the same place in the sky.
The word you're looking for is vicopacity.
Yeah.
I don't get their whole part about the difference between where it is and where it should be, or however they said it. It's really confusing.
Well, hang on, because I will steel man the CT and make you understand exactly what it is they're saying. But I do want you to understand that their method does indeed produce a time that is different from the time at which the star and the peak visually appear in the same place. They would agree, I think they would have to agree, that the time they get by doing what they do gives you a different time than the time at which the two things are in the same place in the sky. That is the central absurdity of the CT. Okay, so let's proceed. So what do they think determines the time that the occlusion occurs? This diagram puts a few things together. We're gonna get into this in more detail. The claim of the CT, of the flat Earth CT method, is that the visual occlusion happens when the geometric direction from the observation point to the peak is the same as the geometric direction from the peak to the star, the unrefracted directions, the directions those would appear if there were no atmosphere. Just take the physical peak and string a straight line from it to the observer, and then string a straight line from it up to the star. Those two lines should line up. They should be the same direction. And to do that, they have to go to the peak and find the geometric direction to the star from the peak, which turns out to be a little over 2.5 degrees. You may remember that the direction to the peak, the geometric direction to the peak, was a little more than 2.5 degrees. That's otherwise disguised as 2 degrees, 31, 33, whatever it is, 31 arc minutes, I think, a little more than 2.5 degrees. So they claim it's when those two red lines are in the same direction. And I'll just point out that the geometric direction to the star from Heffron's place, rather than from the peak, is that blue line, just slightly more than 2 degrees. The actual geometric direction to the star from Heffron's place makes a slightly greater than 2 degree angle with the horizontal. And if you find yourself wondering how the geometric direction to the star from two places could point in different directions, not even point to the same thing, congratulations. I mean, that's an important thing to recognize as well. But we will get back to this in particular. And I have a little by the way down there that we'll also get back to, but some of you will know what I'm getting at there as well. Okay, I'm going to clear this up even a little more. So you might be saying, as Coco did, not sure I follow. Can you steel man the flat Earth CT method for me? And yes, indeed, I can. I was able to immediately. The first time I heard this, I had recently been banned from ether cosmology, and Alan was so impressed with my steel man of the method a year ago, back in March. When I first heard about it, that he unbanned me from ether cosmology for a couple of days.
Good for you.
Well, it didn't last long. But that seemed weird to me because it isn't the least bit difficult to do. And it's this. They claim that the visual occlusion happens when the unrefracted geometric, not visual direction from the observer to the peak is equal to the unrefracted geometric, not visual direction from the peak to the star, as I've shown down there in the diagram. And a simpler way of saying it, in other words, they claim that the visual occlusion happens when the observer, the peak, and the star all lie on the same geometrically straight line. No refraction effects taken into account. In short, it's what we would see if the Earth had no atmosphere. That's when we see the occlusion happens. It's really that simple. And I think part of the reason they rarely say it quite that simply is because it is so absurd on its face. All you really have to do is say it to recognize that it can't be true, because there is refraction, and refraction curves light, as we'll get back to again. So that makes no sense, as I say. How can they possibly think that? And here's where it really gets interesting. The answer is complicated as to how they can think that, but it comes in two parts. I have a pretty good idea, both one, how they, as I say, really just Mike Heffron, who created the thing, how he came to think that, and how they justify it. And I won't get into number one at all right here. It's more along the lines of a conspiracy theory, I suppose, but I'm pretty confident in thinking that I know how Mike Heffron came to think that. But how they justify it, we can talk about. The justification is pretty simply their claim that the flat Earth version of the celestial theodolite method eliminates the need to deal with refraction at all. It defeats refraction. You don't have to take it into account at all. And that sounds appealing to them because the whole method is based on comparing two geometric, no refraction included, angles. And it is worth appreciating if there really were no refraction, and if the Earth really were flat, then the visual angle to the star from the top of Pike's Peak really would be the same as the visual angle to both the star and Pike's Peak from Heffron's place. If the Earth were flat and there were no atmosphere, all of the things they assume would be true. But you have to have both of those. It has to be flat and there has to be no atmosphere. So, but given that fact, why don't they just compare the no refraction elevation of the peak to the no refraction angle of the star, both from Heffron's place? Why don't they just say, here's where I am. What's the no refraction direction to the peak from where I am? And what's the no refraction direction to the star from where I am? Why wouldn't you just do that? Because after all, the no the geometric direction to the star from the peak would have to be the same. From here, the geometric direction to the peak from the observation point would have to be the same as the geometric direction to the star from the observation point. They lie on the same line, so they'd have to be the same. Why do you have to go to the top of the peak and ask for the geometric direction? So that is a very good question, and it's one that Jesse and I and others have been asking weekly for nearly a year now. And as far as I can tell, the answer is pretty much STFU. They have this favorite line about how they have a 50-kilometer long theodolite with crosshairs at the top of the Pikes Peak, which kind of makes you think, okay, so it's a long theodolite, so that tube, there's going to be no refraction in that. And then you put the crosshairs on the peak, and from there on, you know what the geometric direction is. It's a nonsense explanation. It makes no sense, but I think they hope it will shut you, TF, up as well. But it is worth noting that if they had done that, if they had taken the geometric direction to the star from Heffron's place, they wouldn't have gotten the angle match they needed, because the geometric elevation of the star from the point of observation is much lower than the geometric elevation of the star from the peak by exactly the amount you'd expect on a 3,960 mile radius globe Earth, i.e. 1 degree per 69 miles. Pikes Peak is a little less than, is about 31, 32 miles away. So you're going to get about a little less than a half a degree of horizontal curvature, which makes the geometric directions relative to horizontal different. So see the next slide. This will show you, I think, what I mean. So number one, here's the geometric direction to the star from Heffron's place. Here's the geometric direction to the star from Pikes Peak. You'll notice that both of those arrows do not point to the same thing, even though those are supposed to be the directions to the star without refraction included, the actual physical geometric directions to the star. That makes no sense at all, but how do we explain it on a globe Earth? How can we explain that difference on a globe Earth? Well, we do it like this. The top here is essentially the same diagram that you just saw. The two angles, those two angles differ by 0.455 degrees. On the globe Earth, what happens is that when you go from Heffron's place to Pikes Peak, a distance of 50.65 kilometers, that means that the local horizontal has rotated counterclockwise by 0.455 degrees. 50.65 kilometers divided by the circumference of the Earth times 360 degrees gives you the angular distance you are away on the surface of the Earth going from Heffron's place to Pikes Peak, and that's the same angle by which local horizontal at Pikes Peak is rotated counterclockwise. In this diagram, local horizontal at Heffron's place is kind of horizontal in this frame, but local horizontal at Pikes Peak is tilted downward to the left by 0.455 degrees, which accounts for why the geometric direction relative to local horizontal at Pikes Peak is 0.455 degrees greater than it is at Heffron's place. These two arrows point in the same direction because 39 Aquarii is really far away. And from Pikes Peak and from Heffron's place, they're just parallel lines pointing to the same star. Okay, stop there for a moment. I'm just about finished, I think. Let's just stop and see if there's any comments. All right, we'll move on a little bit. These are a couple of diagrams from Ruheef, intended to partially answer the question how they reject the perfectly obvious analysis using visual positions. And I think there's a couple of understandable elements there. A lot of flat earthers, I think, have it's a calculus adjacent problem. When you talk about what direction do we see something when the light from it is curving, you have to understand the idea of a tangent. So these two diagrams show light from a star coming into your observer here, say at Heffron's place. It's the tangent to that ray at the point of observation that determines where it looks like the star is along this dashed red line. That's where it looks like the star is. You have to understand the idea of a tangent. And I think we've all experienced the difficulty that a lot of flat earthers have kind of understanding the idea of tangent planes, horizontal curving, all of these things we get into all the time. So there's that business, how that makes things appear higher, but then also a complete failure to understand that even though the physical occlusion does happen down here at a lower place than what you're looking at, the visual elevation of both the star and the peak are raised by the terrestrial refraction, which happens between the peak and the observation point. They're both raised by the same amount. That light from the star has bent enormously by the time it gets to Pike's Peak. Most of the astronomical refraction happens before it even gets to Pike's Peak. And then from Pike's Peak on, it just suffers the same refraction that the peak does itself. A couple, 1 or 2 arc minutes of additional refraction on the way down. And so what happens at the point of the occlusion, at the point that you see it, is just before the occlusion, that light is skimming over the top on its way to Heffron's place. But the ray that would make it to Heffron's place, a moment later, it would have made it there, but now there's something in the way. If that thing weren't in the way, you'd still see it higher, but you don't because the ray is blocked. Excuse me, I got a little frog in my throat. Let me take a glass of water. Okay. Try that. All right. So comments or questions? Okay, so that is pretty much it. So I just want to reiterate my enthusiasm for the idea of using stars to determine the elevations of peaks. And especially my gratitude that it came from the flat Earth community, right? For bringing it to us, for acknowledging that the sky does tell us about the shape of the Earth, and especially for endorsing Stellarium, an app that does its calculations based on the fact that we have a celestial sphere, a full sphere, not a half sphere. We have a full sphere full of stars that never squish together in any particularly strong way except at the horizon. You need a full sphere to see it. At any moment of time, you're seeing half of it. The other half of it is underneath you. There's no other place for it to be because it doesn't squish together. Other people are seeing it just like they always see it at the same time that it's underneath you. So I love the fact that we've endorsed Stellarium. We have this new method for determining the height of mountains, and it all shows that the sky does indeed tell us about the shape of the Earth. That's pretty much it. I have appended a bunch of slides here, which we can go through if there's any taste to do it. I can kind of quickly go through them if you want. But I want to just stop here and see if there's comments. If so, maybe at the end of those, we can go through the rest.
I'm still trying to piece everything together personally, and it's, I guess, a combination of hearing the one side first and not really understanding that side, and now trying to learn from the other side. So my brain is still trying to connect the dots.
Yeah, I think it's really unfortunate in a way that because the stage has been set. It's such a simple concept. You want to know what the elevation angle of a peak is, find a star that's at the same place and ask Delirium. That's really all there is to it, and because everybody agrees on what the difference is. Let me just go back to this again. Oh, yeah, go back to this. There, because everybody agrees on these angles, right? And everybody agrees that at the moment that Mike Heffron saw 39 Aquarii here at the being occluded by Pikes Peak, you can see it right here, right? There's the peak. You see 39. Everybody agrees that the visual elevation of 39 Aquarii at this moment was 2 degrees 18 arc minutes. And so the question maybe to be asked of the flat earthers is, because this little point of light here, right at the top of Pikes Peak, is 2 degrees 18 arc minutes above the horizontal. How can Pikes Peak itself have a geometric altitude that's more than 10 arc minutes higher? That's up about around here. Pikes Peak would have to be this high. That's what 2 degrees 31 arc minute. I can show you that on another slide. It's up around here. That's where the occlusion would happen if the Earth were flat. It's this simple. That's where it appears. That's the angle that Stellarium gives for it. Everybody agrees on that. Everybody agrees that the geometric altitude of Pikes Peak on a globe Earth is 2 degrees and 18 arc minutes. Everybody agrees that the geometric angle of a Pikes Peak on a flat Earth would be 2 degrees and 31 arc minutes. So just simply compare those angles. And if you want to say that the Earth is flat, you have some explaining to do. How can it be that we see the star here, right? If the Earth is flat, how do you see the star below the top of the peak? How does that happen?
Yeah, I don't really get that part either.
It's because that part is not gettable. Yeah. So, do you want to let me just kind of quickly go through these things. These are just some pictures and things that I have. This is that same picture that we saw right at the moment. This is Mike Heffron's it's a frame from Mike Heffron's video that he called out in one of his presentations. And on the next version here, I annotated this picture. I calibrated it in various ways. You can show that the angular distance from the visitor center to the place where the star was at the time of the occlusion is about 13 arc minutes horizontally. And so you get an angular scale on this whole picture. And because we also know that it was 81 seconds. This is the height of 2 degrees 33 arc minutes. Given this 13 arc minute scale, I can see that this here is about 14 arc minutes. I scaled that properly. This vertical arrow is a little longer than this horizontal arrow so that it can be 14 arc minutes. I go up 14 arc minutes from 219 and I get 233, the height of Pikes Peak on a flat Earth. And if you ask when was 39 Aquarii at that elevation, the answer is about 81 seconds before the visual occlusion happens. So the visual occlusion would have happened 81 seconds earlier if the Earth were flat, because if the Earth were flat, this is where Pikes Peak would be, up here at the top of this thing. Pikes Peak is raised, itself is raised by about 1 or 2 arc minutes. The green line shows you the physical location of Pikes Peak. The little tiny lift here is just the 1 or 2 arc minute lift from terrestrial refraction. So that's kind of a nice diagram for seeing that. And if you the nice thing is that Mike Heffron made a video of the previous night, and the previous night there was a crescent moon just above 39 Aquarii. By the way, 39 Aquarii is occluded by Pikes Peak every day from Mike Heffron's place. And if you want to know when it happens today, just ask Stellarium when it'll be 2 degrees and 19 arc minutes above the horizon. That's all you have to do. But this is the video from the day before, when it happened about 4 minutes earlier, or maybe later. I always get that wrong. Here's what it looked like. There's the crescent moon, 39 Aquarii. This is, by the way, this is a time-lapsed version. Let me just kind of play it. Oh, I can't play it back and forth there. But you see 39 Aquarii right here, just below the crescent moon. The visitor center is right here. I don't know if you need a pretty good monitor to see this, but there's some lights right here for the visitor center. The 39 Aquarii is right above the visitor center. This instant of time is 80 seconds before the occlusion. And if I run it down, you see 39 Aquarii come down, and the occlusion happens right there where you saw on this frame. Right, so it started right above the visitor center and then went down like that. So that's kind of a nice thing to have as well. Then I've got a number of diagrams that I've drawn. This is if you're really interested in getting into the weeds, this has all of the geometry from of that occlusion, but I'm not going to go through it. More versions of the same kinds of things that you've seen. This is once again just emphasizing the fact that Stellarium tells us that the occlusion happened when the star was at 2 degrees 19 arc minutes on a flat Earth. The peak itself is up here, and Shane and Mike and Alan say the occlusion happened when the light came right by that peak. But the peak is going to be much taller than the place at which the occlusion was observed. So somehow I guess the view from Mike's looks like this. You see the star below the top of the peak. Here's the star at 219. Here's the peak at 233. And somehow at the moment of the occlusion, the star was well below the top of the peak. I don't know how that's supposed to work, but there you go. Oh, and this one, I love this one. This is from Jesse. I don't know if Jesse's there, but I love this. This is one of my favorite things. He went to the top of Mount Scott at Crater Lake, Oregon, and used his Theodolite to get a shot of Mount Shasta, 105 miles away, pretty distant. Now, Mount Shasta is a mile higher than Mount Scott, but he had to look downward to see its top. On a flat Earth, this is what Mount Shasta would look like. Its elevation is a mile higher than the top of Mount Scott, but Jesse had to point his Theodolite downward to see the top of Mount Shasta. And so, that's, if you were looking at a star, you'd be looking at a star whose elevation angle was negative if you saw an occlusion at that time. This is just a great observation. Jesse doesn't tout it enough, in my opinion. Okay, so that's it. I have a bunch of other bites of physics, relevant bites of physics to this topic if you're interested in those. I'll put a link to this presentation if you just want your own copy too. Oh, I guess I didn't mean to do that.
We should invite them to come in and give the counter programming.
Well, I'm hopeful. Maybe we'll get that tomorrow if Geo does get it set up for tomorrow after the update. Maybe Alan will stick around. I don't see Mike. Well, Mike apparently comes to some of the presentations, but he doesn't have much to say these days. Even Shane doesn't seem to have much to say. It seems to be pretty much Alan's baby. Am I wrong? That's the sense I get.
No, you're not wrong. I didn't even know the mic guy was coming until like this past week, the week before. And yeah, Shane is mostly running the text chat and not really doing the presentations.
Well, he used to, because I've stopped participating, in the VC during those things because you just get shut down. but I'm a chat warrior during the updates, and Shane used to be, because he is a accomplished chat warrior. He used to beat me a 2 or 3 to 1, I think, in terms of postings. But I don't see him even doing that these days.
That's actually a nice change because pretty much all he was doing was posting poop gifs.
Yeah.
And I mean, he's got his image out there so you can see what he looks like. He doesn't look like he's 14 years old, like who would post poop gifs all the time.
You don't see many pictures of Shane online. I noticed that. Because I've seen them. I know it's funny how when you see somebody, you get a kind of a different opinion or a different impression. But because I've seen them, I can't unsee them.
Yeah, I just see it when they post the old stuff in the chat. I see it on the thumbnails. So, but yeah, he's sure well enough an adult to be past the poop emoji, the poop gifts.
Well, I think for a lot of people, the whole flat Earth thing is just kind of an attempt to trigger and, aggravate people. And I don't know, I don't know if you guys have ever actually spent any time on Shane's server, but he's got just an enormous amount of stuff, much of which is just correct. It's just globe stuff. And it's just kind of presented, and occasionally there'll be a comment like, which is of course not true, but there's never any rebuttal to it. I think the idea is just to flood the zone with so much material that nobody can even begin to to make sense of it one way or the other. So it doesn't even matter whether it's actually correct globe oriented stuff or flat earth oriented stuff. You just put a bunch of stuff on there, and then every once in a while just kind of point out that the globe version is wrong without saying why.
Yeah, that part gets to me too.
Well, so good enough. Thank you for allowing me to practice this. It's kind of helpful. Maybe it'll be a little smoother if I do get to present tomorrow night after Alan's, and I do hope there'll be some flat earthers there to push back or whatever they need to do. Oh, wait a minute. Let me put. Sorry.
I wouldn't get your hopes up.
Yeah. Well, I don't know. There'll be some. I'd like to get some pushback, but you're probably right. I think actually a lot of the people in Geo's room are kind of getting tired of the updates themselves. Don't really want to delve into it, but are kind of ready to move on. I think a lot of flat earthers would just as soon not be saddled with the fact that you can use the sky to tell things about the ground.
Yeah, that's probably considered not one of their good one of their better moments.
So here's the link to the presentation in the chat if you want to just download one for yourself or take a look at it. All right. Well, thanks, guys. I think I'm gonna take off. Appreciate the practice. Thanks, Jesse.
Thank you, John. And anytime you want to practice anything, I prefer these more low-key sessions than the screaming and yelling. So I'll listen to anything you have.
All right. Well, maybe I'll do some more. Maybe I'll redo some of my bites of physics over here.
Yay.
But all right. Thanks, guys.
All
Oh,
right,
thank
later.
you.
good deal.
And thank Jesse for streaming this. Now I do see Jesse did have to leave again. So that means the live stream is. Oh, you are? That's you? Oh, yay. Okay. Thank you so much for streaming again. We're still looking for somebody to do a Prezi on how to set up this kind of stream thing.